So, hi everyone. Welcome to the Hitchhiker's Guide to Rheology. And today we're gonna welcome Camille. She's gonna talk about. Can you just swap
Yeah,
me?
sorry.
Yeah. She's a PhD student at the IFP Énergie Nouvelle, and she's gonna talk about interfacial properties with the microfluidic tensiometer. So yeah, we had a discussion last 2 weeks ago about something that was the like quite close to that subject, and I'm very happy that we're gonna dig into this kind of physics today. So thank you, Camille, for joining us. Thank you for sharing your subject. But first of all, I want to ask you, like, why did you choose to do a thesis on rheology? And yeah, what year are you? And also, what do you want to do after? Yeah, let's introduce yourself.
Thank you, Leah, for the introduction. So I'm almost in my third year of PhD now, and well, I really liked the science, and especially interfacial properties when I was working in my internship before. Because I also did an internship in IFPN.
Okay.
It was more about like fluid mechanics and stuff, but still with microfluidics. So I first kind of came across microfluidics, and then it was mostly related to rheology, of course.
Okay.
Um, but but yeah, so I'm gonna. I wish I could continue doing research after my PhD, and why not do a postdoc? I don't know where, but
Okay,
for now I'm
academia.
just
So
finishing it.
yeah. Okay.
Finishing first. Yeah.
Very nice. Thank you. Yeah.
And where did you do your studies, bachelor's and master's?
Oh yeah. So I did at the engineering school called Chimie Paris Tech in France, Paris, and I also have a master degree in research in microfluidics from the University of PSL. And so yeah, and I did an internship in IFPN and also in ENS for a few months. So yeah, I was always kind of around researchers and stuff because Chimie Paris is also a well-known research center, and so I guess that's how I wanted to pursue in the research.
Cool, thanks.
Thank you. Just to warn a bit everyone, Camille is she's okay with you asking question during her talk. So do not hesitate. Just raise your hand emoji, and yeah, you can just interrupt her during the talk. So that is a bit more like of a
Yeah,
discussion and so
discussion. Yeah,
on. Yeah. Thank you,
yeah.
Camille. You can share your slide, and
Okay.
we're happy to listen to you today.
Or if
Yeah,
you're shy, you can also ask questions in the chat and we're gonna read them out.
Yeah.
yeah. Don't hesitate to ask question
Mm.
because it's not so I'm going to do a talk. It's not completely rheology like as a way you see it, most of people, I would say. So it's mostly on interfacial properties, which is still a bit rheology. But I'm not doing classical rheology at interfaces. Um, so my talk would be kind of in two parts. The first part is really like an introduction to surfactant mass transport, but because that's what we are going to discuss today, um, because I'm going to show you study of dynamic interfacial properties with a microfluidic tensiometer, and I study surfactants basically in aqueous solutions. So the first part would be about yeah, an introduction to this topic, and then I will show you the first results of my thesis. So why are we interested in surfactants in IFP and in general? Is because surfactants actually play a very crucial role in many industrial processes optimization. For instance, with interfaces creation in liquid-liquid or liquid-gas, so emulsions of foams, and also in interfaces reduction. So surfactants are kind of everywhere in industry, whereas it's emulsions in the pharmaceutics, oil companies, or pharmaceutics and cosmetics and food industry. So there are a lot of surfactants everywhere. Actually, proteins can also be considered as sometimes surface active agents. And so we are interested on how it behaves at the interface. And most precisely, we are interested in the timescales of droplet and bubble formation in my case, because we want to optimize processes. And so to do so, we need to understand what happens during the formation of droplets and bubble, which is around 1 to 10 milliseconds. So it's very fast. So we are going to talk mostly about interfacial tension. So I hope everyone is kind of good with that. So I will explain it a bit afterwards. And so this interfacial tension is really dependent on the surfactant mass transfer. And so we need to characterize this surfactant mass transport at timescales relevant for processes. So in our cases, around 1 to 10 milliseconds. Okay, so when we talk about surfactant, when we talk about interfacial properties, we always kind of assume that we have an interface. So an interface is kind of constituted of two liquids or gas, which are not miscible. And so there is like an energy, sorry, at the interface, which can be defined by the interfacial tension. And so what we do is that we put surfactants in one in one part, and they are going to move across the surface and then reduce the interfacial tension. And so it's really a two-step mechanism. So first, we have the transport between the bulk, so where we have all the surfactants, to the interface, which is usually done by diffusion or convection, depending on the process that we are. And then we have the step of the transfer from just below the interface that we're going to call the subsurface to the interfacial region. So this is the step where actually the surfactants that are composed of a polar head and an aliphatic chain, they're going to rearrange themselves at the interface to reduce this energy barrier called the interfacial tension. So here we have three main concentrations that we're going to use later. We have the concentration of the bulk in the bulk. Then here, due to diffusion or other mechanism, we have a slightly different concentration in the subsurface, which is also driven by the adsorption or desorption of the surfactants at the interface. And we have the surface coverage, which is the big gamma, which is basically the concentration at the interface of surfactants. When the surfactants adsorb at the interface, then we have this big gamma, which is going to increase, and so it's going to reduce the interfacial tension. So basically, that's the two steps that we're going to study here. With these two steps, we have also characteristics times. So we have the equilibration of the interface, which is mostly very, very fast, always. Then we have the characteristic time of adsorption desorption, which is the exchange between the surface and the subsurface. So we'll see that we have, in some cases, differences in these times. And then we have the surfactant mass transport from the bulk to the interface, which is characterized by the diffusion time, diffusion convection. And the question is, when we do industrial processes or when we do an experiment, which step is limiting the mass transport of the surfactants? And so it really depends also on the experimental time that we're going to call Tx. So first, if we have a very long experiment, most of the case is just like all the characteristic timescales are very short compared to the experiment times, and so we are at equilibrium. It's mostly what happens when we study coalescence or system at equilibrium. We already are very far after these processes, so we cannot see anything just equilibrium state. Then sometimes we are in an experiment where actually these two, the equilibration time and the adsorption-desorption time, are very fast compared to the experiments. And so we can almost always say that it's instant transfer at the interface. And it's in this case, we are in a diffusion limited system, which means that the surfactants takes a lot of time to diffuse from the bulk to the interface. And then when it's in the subsurface, it's just instant. Then we have also the other case that usually when we have high convection, for instance, it's really easy for the surfactants to go to the subsurface. It's very short, but then we have sometimes also big energy barriers to overcome at the interface. And in this case, it's the adsorption-desorption is the limiting step. Well, and sometimes we have all the mechanism in the same order of magnitude of times. And so in these cases, we can see diffusion and adsorption-desorption. So it's really important to understand in which case we are doing the experiment. And I will show you later, but what we really want to understand in my thesis is this step, the adsorption-desorption step, because in most classical methods, it's always kind of instantly done. And we want to see the kinetics actually of this step. But first, how do we do that? Actually, we need to measure something. And so what we do is we measure the interfacial tension because it gives you actually this surface coverage and the rate. And what we do is we do measurements of interfacial tension during time. But as you can see, all these variables need to be linked with the interfacial tension. And so hopefully we have the Gibbs isotherm that give us, so it's a thermodynamic law that actually give us the link between the interfacial tension, the concentration of the subsurface, and the surface coverage. What we do usually in the literature is that we assume that it's a equilibrium relation. So between really at this interface is always kind of reached. And so we use the Gibbs isotherm every time. It's the most common thing to do. And so what we are going to do. So the first thing, I will show you some equations. You don't need to understand all of them, but it's important to see that the equations are not that simple, especially for diffusion and the other mechanism. And that are the equations that I use to create my models with my experimental data, and I compare them. So it's the second part, but you need a bit of the background, theoretical background. So when we are in a diffusion limited system, so as I said, this step of adsorption-desorption is very fast, equilibrium is very fast, so we say it's instant. Then we are in a diffusive system. We have the work of Ward and Tordai, which is actually quite old, from the 40s. And they described this step of diffusion from the bulk to the subsurface. And so you have this equation with the coefficient diffusion. And then here you can see the dependence of the concentration of the subsurface. And this is always a bit difficult to translate. But here, if we are in a diffusion limited step, then the subsurface is almost, it's the same here. And so we have here about the surface coverage. So again, all the mass transport equations are kind of written with the surface coverage, and then we need to link them with the interfacial tension. Then we have the kinetically limited model. And so here in this part, we assume that we have no diffusion. It's only the step of adsorption-desorption. And we have several models. We have this one of the simplest, rather the most used one, is the Langmuir model. So we kind of consider the interface as small sites that are at the beginning empty, and then we assume that we have the same probability for the surfactants to go to the interface. So probability of adsorption is independent of everything else and independent of the occupancy of the neighboring sites, which is really important. And there are no interactions between all the molecules. So this is a very simple model for Langmuir, especially when we work with proteins, for instance. The Langmuir never works because they have a lot of interactions between the molecules. And so it's basically diffusion, like something like that. Yeah, Emilia, I think you have a question.
Emilia,
Um,
Emilia, you can just unmute yourself and ask the question if you want, or write it down in the chat.
Oh, sorry, I thought I was already on mute. Classic. Hi. When you were diffusion limited, so in the previous
yes.
case, just because I don't see if there's geometric, well, I do see there are some geometric for the diffusion, but well, what is the hypothesis in terms of the size and shape, I guess, of your surfactant molecules?
So here in the diffusion process, so yeah, there's some people have shown that there are some, of course, an influence of the curvature of the interface. But then about the surfactants is mostly the shape or the bigger the shape of the molecules is always kind of hidden in the diffusion coefficient. Like if you have a bigger molecules compared to a smaller one, they won't have the same diffusion coefficient. Then the geometry, what they do at the interface is not taken into account here, because here is only the diffusion step, and we suppose that at the interface everything is adsorbed instantly. And
Okay.
and so yeah, but here you can see, yeah, of course, if you have a very curved interface, for instance, if you do a rising droplet or a pendant drop or something like that, then the interface is not always completely plan.
Okay, and
I
just
hope,
because the Gibbs isotherm doesn't really consider that diffusion coefficient, does it?
So the Gibbs isotherm is mostly just used to link the surface coverage to the interfacial tension, because like the easiest way to understand and to study surfactant mass transport is really to measure its interfacial tension through time. There are also some other methods, like you can kind of deduce the surface coverage directly, and the link between surface coverage and interfacial tension can be found experimentally, but it's much more difficult. And what we do in the literature mostly is use the Gibbs isotherm in every case, actually.
Okay, thanks.
And so in the kinetically limited here, we do not have the diffusion as is just discussed before. And in this case, it's just, so the Langmuir is very easy. It's kind of first law kinetics, and we just have the surface coverage easily. And then again, we use the Gibbs isotherm to link both of these parameters, and then we have a simple law for the interfacial tension. So this is the one that is the most kind of used, and this is describing only the adsorption-desorption step. We have also the model of Franklin. I will not completely discuss everything, but as you can see, it's basically the same thing. Just the Franklin model includes an interaction term at the interface, because in the Langmuir we said that the molecules do not see each other, basically. In the Franklin, he just add a term to say that probably the surfactants are actually interacting with each other. But it's not the most complicated model also. And again, we use this equation to have the equation of state, and we have that. And so it's a bit more difficult. And of course, so this is the two kind of extreme conditions. But then if we have a mixed model, then you need to use the kinetics at some point to have the concentration in the subsurface, and also the diffusion equation. You have to mix both equations to have the final big equation of state of the interface. And so this is a bit more tricky, actually. Okay, so let's talk about the methods now. So as I said, we have this kind of big theoretical models that are actually a bit old but still used. And then for the experimental tools, we have, you've probably all heard of the rising drop, pendant drop, or Wilhelmy plate methods, which are three main methods that are a lot used in the literature to measure interfacial tension. And so we need to measure interfacial tension through time. And so with these classical tensiometers, we have precise measurements for time above 2 seconds, mostly. And the problem with that is that adsorption and diffusion mechanisms are usually non-dissociated, and we are mostly in a system which is driven by diffusion, actually, because we have high timescales, and we have high bulk. Like compared to microfluidics, you have just imagine that the time the surfactant travels from this point to the other is much more longer than the one they have to absorb. And so that's the tricky thing, because in industrial processes, we need to know what happens at these very short timescales. Because when we form a droplet or a bubble, it's really short. And so we need to have the value of the interfacial tension at this point, which we cannot completely grasp with classical tensiometers. And that's when we go to microfluidic devices, actually. I don't know why it's in. Okay. Well, if you want to know a bit more about all of this background, theoretical and more complicated models, we've written a review this year. It was published in June. And so I discuss also a lot of the different microfluidic devices, because today I'm going to show you just one. But in the literature, there are already some people that are doing kind of the same measurements and try to understand these mechanisms and to measure interfacial tension with microfluidics. So in my PhD, the idea is to really understand both mechanisms separately. And so not only the diffusion that we can grasp with for instance, the rising drop, but also the adsorption limited conditions, because we want to really characterize also the kinetics at the during the adsorption and desorption step. So we actually combine both methods. So the first method, really well known and really used, is the classical method of the rising drop. So I use the automated drop tensiometer from Tickless Instruments. And we have the timescales above 2 seconds, and we are mostly in diffusion limited conditions. And then on the other hand, so I work with microfluidics, and then here we are able to go to very short timescales, and we are mostly in adsorption limited condition. And for these experiments, I went to the Netherlands, and so I used the edge tensiometer developed in Wageningen University and Research. So it was part of a collaboration with them. And so I used this chip, so I will present it just later. And for the system, I just choose classical non-ionic surfactants at the water-oil interface. I'm sorry, I won't be able to tell you the name of the surfactants because we are under publication and confidentiality thing. But basically, it's just non-ionic surfactants, and it's classical one. So let me show you the edge tensiometer. So here we are at very small scales. So we have a microchips, which is composed of two main channels, one with the surfactant solution in water and then the oil, pure oil. And what we do is that we create small droplets at this plateau. And so we have small pores, and then we push the oil through the pores with pressure controllers to form these droplets. About the dimension, you can see that just the width of the pore is 14 micrometers. It's basically, yeah, like your hair is around, yeah, the same size, 10 to 20 micrometers, the hair. So it's really, really small. Of course, to see everything, we use a microscope. And so, as I said, we work with pressure controllers, and we fix both of the phases. What is really important here is that by have these pressures, we have the effective pressure at each pore and PD star, and this is what we're going to use to actually measure interfacial tension. So here is a small video. So above here, you have the continuous phase flowing with the water and the surfactants, and here the dispersed phase going through the pores. So what happens actually? The thing is like the formation of the droplets occurs when the effective pressure, so the PD star I showed you just before, exerted on each interface, so each meniscus here, exceeds the Laplace pressure. So when we go above the Laplace pressure, then we have the formation of the droplets. And so this is what we use to determine the interfacial tension. So we basically change the PD star value by changing the pressure of the dispersed phase. And then when we have these small droplets, we know that we have overcome this Laplace pressure, and we know that the interface, we have this interfacial tension. And so for each PD stars, we have a value of the interfacial tension. And then about the time, we need to look a bit more into detail about this formation of the droplets. So at the beginning, we suppose we have a naked interface without any surfactants. And then the surfactant starts to arrive from the continuous phase flowing. And at some point, when we overcome the Laplace pressure, so when we reach the speedy stars and this interfacial tension, then we have, because the surfactants absorb to the interface, we have the reduction of the interfacial tension, and therefore we decrease also the Laplace pressure. And this is how we can, the oil can flow through the pores and form the droplets. So here, basically, you can see that at some point, it's going to flow and form the droplet. And here, for instance, up, the droplet is formed. So the moment between this time and the moment the droplet is formed is the adsorption time of the surfactant. And so what we do is basically, I count the droplet. So I put a dispersed, the pressure of the dispersed phase, and then I count the droplets within a certain amount of time, and I have the interfacial tension through time. So it's actually quite easy to measure. And then we can basically have the whole curve for that. So I don't know if you have any questions about this part, because I know it's a bit tricky to understand. So if you have some, don't hesitate. Okay. So as I said, the interfacial tension is determined with the Laplace pressure, and the adsorption time is linked to the droplet formation frequency. And so now I can show you the results that I have with the edge tensiometer. So first, I've studied different surfactants so A and B, let's say, different concentrations. So I always put as a fraction of the CMC. So the CMC is the critical micellar concentration. So above the CMC, we have micelles forming. And so above, we have diluted concentration. So here I have my surfactant A. So as you can see, we have first very short time scales. So it's about 10 milliseconds, the beginning. And we can go to above 10 seconds, actually. So we can reach some range of time that we cannot reach with the classical tensiometer. What we can also observe is that when we increase the concentration, then the kinetics goes faster. So which is also kind of normal, I would say, because we have more surfactants, and so the interfacial tension reduces more rapidly.
I do have one question.
Yes.
What if you increase again the concentration when do you reach a plateau where you cannot shift your curves anymore? Do you have
Well,
instabilities or?
this is what is also very interesting about my results is that we found that with these surfactants and also with others.
Yeah.
So as you can see here, 1 CMC and 2 CMC, we reached the same plateau because we reached the maximum surface coverage.
Yeah.
And so physically, at some point, the interface we cannot stack more surfactants. It cannot absorb more than, I don't know, a certain amount. However, which is really interesting, is that you can still see a shift of kinetics. And actually, when I increased, at some point, I increased up to 10 CMC, I guess.
Yeah.
I could still see the shift of the curve.
Okay.
And so it's something that we haven't understood it yet. We have several theories, like for instance,
Maybe the interaction between the surfactants or
interaction between the surfactants, or well, when we are at 10 CMC, I mean, we can probably say that we have a lot of micelles.
yeah.
But again, if we suppose, and that is something that is mostly done in the literature, that micelles are not so fast active, then it's a bit weird that we have still this shift. So maybe in our cases, either the micelle dissolution is very, very fast, and so we have kind of an increase again of monomers, or either micelles absorb.
Okay.
But again, it's something that we need to understand. But you're right. It's really interesting to see that, and I've seen that with all of the surfactants I've studied. And so it could also mean that we reach such short time scales that we can see other mechanisms that I couldn't see with classical methods.
Tensiometer. Yeah. Okay. Thank you.
And so we compare different also carbon chain lengths. So the surfactant B is a bit bigger. So we have bigger carbon chains. So as you can see, everything is shifted, but the trend is the same. And I did the same with surfactant C, which have a smaller polar head, and it's also a bit shifted. And so as you can see, it works really well with a lot of different surfactants. We have at least 3 decades of interfacial tension, and this is really interesting. But now this is kind of the main like experimental results, but the idea was to understand and to see if we were really in the adsorption limited process or if we had diffusion. And so we decided to compare with also classical tensiometer, as I said, and with theoretical models. So for the rest of the presentation, I was just going to talk about the surfactant A, which is the same, the non-ionic one. All of them are non-ionic, but the A is the one that have most data, I would say. And so I've performed interfacial tension measurements with the rising drop method. So it's called ADT with the tracker. And see here you have also the concentrations. And first, what we can see is that I couldn't have measurements before 2 seconds, which corresponds to the formation of the drop in the rising drop. And so as you can see, you have also, it's faster when we increase the concentration. But here, if you compare to the edge tensiometer, you see first you see it's nice because it's combining all of them. We have the same equilibrium plateau, which is really good. But then if we go to the diluted systems, then we can see that there are a lot of discrepancies, especially for the orange and the yellow curves. Both the orange curve are the same concentration, the same solutions, the same surfactants, but not the same method. Again here. And so this is one argument say that we are not in the same mechanism. We are not in the same limiting step. And we can assure that with the rising drop is mostly diffusion, while it's much faster in the edge tensiometer. And so I plotted the models. So the continuous line is for the diffusion model. So it works mostly nicely at the end of the curves, but always with the tracker, the first points are a bit tricky to to have. And also with the yellow curves, you can see it's mostly driven by diffusion. While you can definitely see a shift of the mechanism with the edge. So in the dotted lines, we have adsorption model. So here I've just plotted the Langmuir model. So it's the simplest model I have. And it works actually nicely for at least, well, the two first concentrations. Then we have a bit of discrepancies here around the little corner. Probably due to the fact that my surfactants actually have interactions between them at the interface. And so that's something I need to work on, like use another model to see if we can account for different mechanism between the monomers or the surfactants. But which is really interesting is that we have the possibility to combine both measurements and see that with the edge, we really have much, yeah, we have access to much shorter timescales than with the classical tensiometers. And also the other thing that is really interesting is that here we can have a proof of a shift of the mechanism, which is, we can also see that as, I don't know if you remember the geometry, but with the rising drop, we have really, the bulk is static, and we can physically understand that we are mostly driven really by the diffusion, while with the edge, we constantly push water, we flow water with surfactants, and so the surfactants are kind of immediately at the interface. We do not have diffusion because also of the flow of the solutions. And so yeah, with the ADT measurements, so the classical one, we are really limited to long time scales. For me, it's long, like above 2 seconds. We see a kinetics only for low concentrations, that we see a really interfacial tension decreasing, because with high concentrations here, we always reach the plateau, almost at the beginning. So we do not see any kinetics. And also we saw that the diffusion model, so I use the water-Tardai theory, is also in good agreement. With the edge microtensiometer, it's possible to reach so around 10 milliseconds for my surfactants. And we see transport kinetics for all the concentrations, even with very concentrated solutions. And for now, the first adsorption model that I've used, so Langmuir, is already in a good approximation with my experimental data. So yeah, this I'm currently writing the article with all these results, and but still we have other things that we want to look into. For instance, with the edge, as we mentioned with Leah, what happens above the CMC, because it's something that it's not really understood. Then I want also to compare with other adsorption or mixed diffusion mechanisms, so Fromkin or other models. And with the tracker measurements, well, I've tried to reach smaller timescales, but it's really, really difficult because we need to account for the adsorption of surfactants during the droplet formation of in the rising drop. And so we are always limited in how fast the droplet is formed during this process. But then at very long time, we can also investigate other mechanisms, especially with my surfactants that are a bit big. So we could probably see some reorganization, but then again, we need to be careful about the impurities. So people that already done some interfacial measurements know it's a bit tricky and that we really don't like impurities during the data. And so yeah, if you want to understand a bit more about that, so as I mentioned, you have the review, and so in this article, I actually compare different other microfluidic devices, not only the Edge, but also the one developed actually here in IFP EN by Marie Marsiglière, who managed to measure ultra-low interfacial tension measurements with another method. And so this paper is the paper of Deng about the edge. And so here everything is explained about the mechanism in the edge. So thank you very much for your attention. If you have any questions, please don't forget to ask. You can also contact me if you want later.
Thank you, Camille, for your presentation. It was very nice. I love whenever there is more and more physics in the rheology. And yeah, this is not quite like the previous session, the previous edition was about more suspension, and I really like your talk. If there is any question, you can go right away. I have a few too. Do not hesitate. You can also write it in the chat if you don't have the mic, or do not hesitate. Oh.
I think you can break the ice.
Yeah. Well, I had a question too, because you showed some contact angle. I guess it's about the interface inside the micro device. I have a question. Have you changed the size of the porous media, like a bit smaller, a bit larger? And just to understand a bit more, like why you have chosen this 40 micrometer, because I guess you need something that is less than the capillary length, of course, of the liquid to create those bubbles. But yeah, I wanted to understand a bit more why you were maybe measuring those or not.
Well, actually, the edge tensiometer at the beginning was built for to create to create emulsions with very, very monodisperse emulsion, actually, with the same size of droplets. Because as you can, well, I don't know if you see here, but the size is always the same. And so it's something that's also very interested in the field. We want to create monodisperse emulsions. And then Boschin Deng in the Netherlands, during her thesis, she actually developed the method to do a tensiometer. So it's mostly the work of Boschin, who actually changed the width of the pores, a bit of the height, and she changed a bit the dimensions, but it was always mostly between 20 and 40 microns of the width. And then in my case, I do not need to have a lot of pores. That also, there are some edge tensiometers you can have in series, uh, like one like that, and just you can follow up with 4 or 5 plateau like that. And so you can have a lot of droplets to create the emulsions too. In my case, it's also like it worked with these dimensions.
Yeah.
It also worked with the 21, but with the 40, it worked really nicely. So I just chose this. And then again, it's not really, well, the dimension we needed to calculate the interfacial tension, but the thing that is really relevant is the pressure that we apply, because this is really what gives you the interfacial tension. Then, of course, the contact angle is important. But then if you take some pictures, you can easily recover the contact angle.
Okay. And what was the pressure that you were, like the capillary pressure that you were imposing on both, like the difference in pressure?
Well, I think it was well, at least 100 millibar, and so 100 to 700 millibar for the PD star.
And so yeah, so you don't have any inertia issues or
No.
dissipation at the solid interface. Oh, okay.
No, exactly. That's the thing that is really nice with this with this with the tensiometer is that actually the interface is it's really interesting because it's just kind of static also. Like the dispersed phase, while we have a pressure, it's not flowing a lot. Like we have this what we call the transition pressure, above which we cannot use the capillary pressure because we are always above it. And I work under this transition pressure. We have another regime afterwards. And so I work in the case, of course, the capillary forces are predominant. Otherwise, yes, you can have some weird stuff and not nice droplets like that.
Thank you very much. Is there any other question? Yeah, can go ahead, Jinesh. Oh, yeah.
Hi. Thank you, Camille. It was a nice presentation. I have one question regarding ultra low IFT. I think so. I'll have to go through that article in the reference you showed. But if you can just give like a quick insight, because if we have ultra low IFT, I believe shape of droplet will be a bit different. So how we will get quick IFTs in that case? And my second question is like you just studied nonionic surfactants. Because let's say if you consider surface excess concentration like Gibbs isotherm, the formula will change, right? So like there will be 2 in the denominator. So other isotherms, or do we have to consider any other parameters for other equations too? Thank you.
So I will answer the last question first. About the Gibbs isotherm, yes. In my case, it's non-ionic. So in my thesis, we chose to actually kind of have the simple systems because it's really difficult already to reach the adsorption step and to measure this step. And then, of course, measurements were done with SDS. And so we didn't plot the model, the theoretical model yet, but the thing is we always use this Gibbs isotherm, but it's not 100%, how do you say it? We do make a hypothesis every time we use it. We do make the hypothesis that for a certain amount of surface coverage, we have the same amount of interfacial tension. So kind of always an equilibrium between these two things, which is probably not exactly the same. It's not always reached. So we have some other papers and other articles that show that actually measure with compression and expansion of bubbles. Usually it's with bubbles. They manage to have to get rid of the Gibbs isotherm and to directly measure surface coverage as a function of interfacial tension. And so for that, they use the area of the bubbles. They do compression, expansion, and it's very nice work, but it's also very time consuming and also something that we really need to look into. It's another kind of study, I would say. But yeah, this is one way to get rid of the Gibbs isotherm. Another way is to kind of use, for instance, another law for the model, because here I base everything on the Langmuir and the Gibbs, but some people just have some empirical laws of exponential decreasing. So yeah, it's always a bit difficult, but most people use the Gibbs isotherm. And then if you use ionic surfactants, you need to change it, of course. And I don't remember the first question, I'm sorry.
Yeah, it was mostly regarding ultra low IFT, like the shape of droplets, like.
Oh, like the shape of the droplets in the edge?
Yes.
Okay. Well, here it's the droplets, as you can see here, it's mostly driven by the height of the pore. The height is around 1 micron. I guess that if you put a bit bigger height, that the size would be a bit different. But the size is also driven by the interfacial tension, which is also driven by the pressure that you apply. And so the pressure that you apply will also be different according to the height, because it also is given in the Laplace pressure. So all the dimensions are in the interfacial tension. I think that here, yeah, I give a simplified formula, but here actually you have also the other. So here I just have this curvature, but you also need to take into account the other one, the one that is in the front of the. Like here, I just use this one, but actually you also need to take into account this one, where the height appears. But here we have a very small height, so we don't really need to take it into account.
Yeah, it's really like a confined flow.
Yeah, it's really confined. Like, I mean, yeah, it's always kind of the same size of droplets because of the dimensions.
Yeah, of course. And just one question, and I don't know if there are any other questions, but I'm curious. You have tried with oil and water, and again, it's already like super great what you have done. But have you tried with any other types of maybe not monomers, but maybe polymers instead of oil, or
Well, actually, Boshin, she did a lot also with air. So she put, so she can also do some water-air interface. I don't think about polymers, because the problem with polymers is that, at least not in the dispersed phase. In the continuous one, I think she also worked a lot with proteins, because in the Netherlands, where they are in Wageningen University Research, they do a lot of work in food engineering and food processes. And so she did a lot of measurement with proteins too. But basically for the dispersed phase, it's always oil or water.
Okay.
And it works kind of nice in any case.
Because as you mentioned, protein, that was like most of the proteins are long chains, and it was like maybe there is an entanglement or any other types of interaction that can be super tricky to tackle. And
yes, yeah, and the thing I think it depends on the protein, I would say, but I guess it worked in any case. But then again, you can check also her work, Boshin Deng. And so she did publish a lot about proteins, if you're interested in that.
I'm gonna check that definitely. Is there any other question in the chat? And if you have question, I don't know, Camille, if you're you've you've put your email address, so I guess you're willing to answer questions
Yeah.
through your email. So again, if you're a bit shy, you can also send an email, I guess.
Yeah, I don't know. I'm just looking. Yeah. If you have any question or via LinkedIn or other
Yeah.
channels.
Well, thanks again, Camille, for your presentation. I think maybe questions will rise through time. And yeah, I'm gonna stop the recording right now and see you in a minute. Bye, YouTube.